All right, let's go ahead and get started. So, a couple of announcements to begin with. So, I've been chatting with a couple of you individually who need to make up labs. And so, tentatively, it sounds like we can do a makeup lab session on, I'm looking at Tuesday, November 22nd. So that would be like during our regular lab time. It's just we don't have lab that week since that's Thanksgiving week, and actually we end, so we're almost to the end of the quarter. So I think we only have, what, one more lab after this week, and then we'll have the lab final in 2 weeks. So just look out for that. Sorry?
We have lab this coming the 13th. Wait.
Sorry, I need
So
to.
I'm in December. Hold on.
So we're almost to the end. So we have this last week of lab. Then next week we'll do one more experiment, I believe. And then after that is the lab final.
The 15th or the 29th?
Wait, we have 2 weeks without lab?
Sorry, I'm trying to
We
pull.
still have labs the week of Thanksgiving, right?
No, there's no lab the week of Thanksgiving.
After the binder test, or the
No.
lab exam.
So we have a week without.
So our final lab is what, December 1st?
Our final lab is next week.
So then our final lab is the 17th? Like the exam?
Y'all are confusing me. All right, so looking at the schedule, I know we're almost to the end. So we're in week 7 right now, so we're doing lab 7, empirical formulas. Next week is our last lab, thermochemistry. And then the week after that, so this is a week before Thanksgiving.
15th.
Yeah, the 15th and the 17th. So this will happen during your regular lab session. It'll probably just be weighted the same amount as a lab report. And it'll be multiple choice, maybe some short answers, thinking about having you do some density stuff in lab for like the real part. And then the rest of it will just be kind of interpreting results. I would expect some calculations, like maybe I would give you data for like this lab that we're doing today, calculating the formula. So if I give you dummy data, can you do it? Something like that. So it should all be stuff that you know, nothing crazy. But that's next week. So that's lab final, and then we'll do drawer checkout, so make sure everything's nice and clean for the stock room for their sanity. And then that's week 10, so we don't have lab that week because of Thanksgiving. And so this will be the makeup week, and we're done after that. So after Thanksgiving, that's exam week, so we're basically at the end. All right, so does that clarify things? Hopefully people aren't too sad that things are coming to the end. So lab final is week 9. So again, lab makeup would be after that. And just email me if you need to make it up. Email me and what lab you need to do, or labs. So again, a few people have talked to me, but let me know by email so I can tell the stockroom what they need to set up or what I need to get out for you. And so with the end of class, don't forget to register. My camera isn't working on OBS since I forgot to fire it up. But I'm wearing my obnoxious green color today to remind you to register.
Is the exam too cumulative?
Chemistry is just cumulative by nature. So I won't like ask you anything explicitly over the previous stuff, but of course all the skills are building, knowing oxidation states, naming, all that just kind of builds. So don't forget to register, and like we said I will give out bonus points. So it'll probably be bonus points on your final exam. So I'm thinking 5+ points. And so again, if you're transferring, if you're graduating, just write me an email.
Will we still get it if we have to wait to register till next week?
Yeah, so I just need an email in by December 2nd. So hopefully everyone can register by December 2nd. And if not, you can just write me an email like, I will register this date so I can give you your 5 bonus points. So I just want to know your plans. Again, if you're taking time off, even just let me know, hey, this is my plan, just so you can get your bonus points.
Thank you.
And so with that, I would also think about, if you need advising from me, let me know. Even if you've talked to your advisor, if you want to chat with me about like making sure you're prepared to transfer, I'm more than happy to chat. Sometimes I don't know that you all get the best information, especially with sciences and like making sure you have all the science courses to transfer. So feel free to chat with me. And then another thing that you should be thinking of as we go into December, so that gives you some time to think about research. So I would definitely look for research opportunities, and whenever you're interested in, there's tons of RU programs. And so look for opportunities. And again, we can chat too, so if you want help looking for research, where to find things, I mean, really a good start is just like the NSF website, and they have a lot of links to resources. And it does take a lot of legwork to comb through like what's accurate and up to date, but there's stuff out there, there's money out there, so you just have to look. And so again, if you want to chat with me about that, I'm more than happy to help y'all, because that's super important for your career, is like just getting in all those experiences, the hands-on, the real stuff, doing the research, or internships or whatever. So I'll put on their internships. So if you're interested in like the business side of things, getting an internship would be really good now. All right, any other questions, comments?
Found my homework, it's in there. Thanks.
And I have a stack of papers to give back, so I'll do that while we're getting the quizzes. All right, so let's finish up chapter 10, and I have homework if people need the homework still. And the polyatomic ion sheet is also up front if you need one.
When we read the polyatomic ions, is the charge always written as part of the formula or part of the?
So I guess so if you just write sulfate, you would have to write SO4 2 minus.
Yes, okay.
Yeah, but then of course you don't want to put the charge like when you're writing. So if you're doing iron sulfate, then you just iron 2 sulfate, then it's just FeSO4.
Because it's got a neutral charge, right?
Yeah, so you don't want to write any charges, but then if I wrote like FeSO4 negative, then that means that this is some sort of charged compound. And something would be weird, so probably this would be, right, iron 1 sulfate ion or something like that. All right, so now we're looking at back to our types of reactions. So quick recap, we had done our synthesis, so that was 2 things coming together. Then we talked about decomposition, so that was something spreading apart. So one compound becoming multiple. I don't know what happened to my slide. So there was our decomposition. So now we're looking at single replacement reactions. And so does this single replacement reaction, does this remind you of some reaction you did in lab? Which reaction do we do in lab? It was a single replacement. So one of the copper ones,
Isn't it the zinc one?
so the zinc one. So what was that reaction? It might even be on here, a similar one. So you said the zinc one. So does that mean zinc was our starting material, part of our starting material?
We added it to it.
Yeah, so we added zinc, metal, and then what did we add it to? Do we remember? Our copper sulfate, so CuSO4. And so we did this reaction, and then what happened? What do we get back out of it?
Zinc, SO4, and copper.
So copper, and then the zinc SO4. So this was a clear example of a single replacement reaction. And so we can see what was going on is we had started with our zinc metal, then it became an ion in solution, and so it was colorless. And as it became colorless, you also formed that copper, rusty looking metal back out. And so now there's another question that I'm going to propose. So what if we had tried kind of the opposite? So what if you had had copper solid plus zinc sulfate? Would anything occur? What do you expect, maybe, just based upon the previous one? So that's what we might expect. But then if this actually occurred, do you think the previous step would work as well as it did and we'd be able to get our copper out? So no, so there must be something that drives this. And so this is where the activity series comes in. And so this is in your book. In hindsight, I probably should have printed one out for y'all, so maybe I will do that while you take your quiz. And so this activity series, it's arranged in increasing activity. And so part of it not only tells us how they react, so let's look at first these descriptions. So we have at the top lithium, potassium, barium, calcium, sodium. And so we know these tend to be very reactive. So they react just with cold water and produce H2, or sometimes with dilute acids. And again, you get that H2 gas. So as we move down this activity series, so now magnesium, aluminum, manganese, zinc, chromium, iron. So these react either with steam or hot water. So now we're noticing, right, they need more energy to keep going. And they still produce H2. Or we need an acid. And then, of course, if we go down, so now we're at cobalt, nickel, tin, lead. So these need acid to react with H2, right? So they're not just going to react with water. So now they're less reactive. We have to add acid to get them to go and then produce H2. And then now at the bottom here, so copper, mercury, and silver, so they are unreactive. So they would not react with water or acid. So you might remember this. You did some reactions trying to dissolve metals in acid. Do you remember that lab? Some nods. So I think you tested like magnesium, zinc, and copper, if I remember correctly. And so if you remember, magnesium probably reacted the fastest and most readily with your acid. And then the zinc kind of looked at you, maybe it kind of bubbled a little. And then the copper was pretty much no reaction. And so basically this has to be done experimentally. So this has been done, and a lot of it has to do with their reduction potentials, which we're not covering right now. So we have to look at this activity series to figure out who's more reactive. And then so the next thing is, so back to this question, well, how do we know which reaction is going to occur other than, of course, doing it? Well, if we consult our little chart, so let's find zinc and let's find copper. So zinc is higher than copper, and any metal that's higher than a metal below it can replace that metal. So looking at this, that means zinc can again replace copper. So looking at this reaction, now we're verifying, okay, this is why this one occurs. So zinc, higher activity, so it knocks copper out, making the zinc sulfate like we saw. And then this reaction, so again, you did a good job of predicting what we might expect, but then if we consult the activity series, well, copper is now below zinc, so no, it can't actually knock it out. So then we would say this is really no reaction, and you could offer an explanation. So copper is below zinc, so therefore it's less reactive, cannot displace it. And so now if we look at these other example reactions here, we can see why these occur. So we have magnesium replaces titanium in this titanium tetrachloride, or that Tickle compound that we had looked at the other day, to make magnesium chloride and titanium. So you'd have to find an activity series with titanium. But you could also guess that this probably occurs, so magnesium is one of those fairly reactive ones, so it makes sense that it would replace it. Trying to find a better one. Well, I'll hunt around for a better one. And so same thing, so this iron can displace our hydrogen. So hydrogen should have been on your chart. So let me add it. So hydrogen falls between lead and copper here. So as long as our metal is higher than hydrogen, it can displace it. And so looking at iron, so iron is over here. And so yes, that would react. So this would go, so it would go like we predict. And so again, it replaces our H2. We form H2 gas there. So looking at this reaction, so copper plus silver nitrate. So does it occur? So looking, oops. So copper is just above silver. So yes, it can displace it. So yes, that reaction occurs to give us our copper nitrate and recovering out our silver. And then of course this last one is very similar to what we did in lab. They just used copper nitrate instead of copper sulfate.
Are there any exceptions to this? Kind of like how there's exceptions to the ionization energy stuff on the periodic table?
I don't think there's really exceptions. Again, just as long as you're consulting a chart that has the metals that you're interested in. And so this was all done experimentally. And then have we talked about redox in here? I don't think we have. Or oxidation states. So single replacement reactions will offer another term. I think this was mentioned, at least in your lab briefly, of redox. And so redox just stands for an oxidation reduction reaction. Well, what the heck is that? And an oxidation reduction reaction involves the transfer of electrons. And so if we analyze this, and it's kind of most obvious in these single replacements since you have something in its elemental form and then you make something else in its elemental form. And so magnesium, anything in its elemental form has an oxidation state of 0. And then, of course, we can use our ions to determine the other ones. So titanium is 4+, chlorine's -1, then magnesium in the product is 2+, chlorine's -1, and then titanium 0 since it's back in its elemental form. And so now we can see that there's electrons moving around. So if magnesium went from a 0 to 2+, that means that it lost electrons since it became more positive. Meanwhile, titanium accepted them, so it became more negative, going from 4+ to 0. So it gained electrons. And then if you wanted to do some electronic bookkeeping, you would see that the electrons should be the same, and so that's the other key. So electrons lost have to equal electrons gained. And we do see that is the case here, so we have one equivalent of titanium, and so it lost 4 electrons, so that was 4 electrons in that process. Now we have magnesium, so we said it went 0 to 2, so each one is losing 2 electrons, but then we have 2 equivalents of magnesium, so 2 times 2 gives us 4 electrons there. And so that makes sense, right? So magnesium is giving those electrons to titanium in the reaction. That is what's going on. So again, you saw that with the copper in lab, so that is how it gives out the metals. It's transferring those electrons, and then that causes the copper to plate out, and meanwhile the magnesium to replace it and become an ion. Does that make sense? And so I don't want to go too much into redox since it's not quite part of this chapter, but it's hard to talk about single replacement without discussing it. And again, you can just kind of see, get the highlights here. We know iron starts off in 0. Now we can tell it's in the 2+ in our compound from the SO4. So you could look up sulfate, find out that it's SO4 2-. So we know iron's in the 2+. And then we added sulfuric acid, so hydrogen. We said that's always 1+, unless we're talking about hydrides. Otherwise 1+. Now H2 in its elemental form goes to 0. So we can see, oh, iron lost electrons and hydrogen gained those electrons. And so that's just repeated down here. So again, I'll just hit the highlights. Copper starts off as 0. Now it's at 2+ in copper nitrate. Silver is 1+, then goes to 0. And then same thing happened, just like you saw in lab. Zinc started off elemental form 0. Copper was 2+, just like it was in your copper sulfate. Then we recovered our copper metal, and of course it's 0 oxidation state, elemental form, and zinc became 2+. And so now looking at this reaction, so we could make a prediction. So this could be something on an exam. So I would just give you the first part, zinc plus the calcium perchlorate. Would it react? And so again, you would consult your chart. There's zinc. Zinc's below calcium. So no reaction would occur. And so this is just other examples of single displacement reactions that you could have. So this is kind of unusual. You have carbon reacting with the iron oxide to give you iron and CO2. So this would be iron 1. So it didn't show what the product is, but iron just went from iron 3 to iron 1+ in this example. Oh, sorry, that's not it. It went to just elemental. The L confused me. My apologies. So I went to iron in just its elemental form. And so the halogens can also do displacement reactions. And so if we look at the halogens, so the activity of the halogens is in this order. So it makes sense, follows the periodic table, so we know fluorine is the most reactive, so we can always replace chlorine or bromine or iodine. And meanwhile, so chlorine, of course, right below fluorine, so it can replace bromine and iodine. Bromine can only replace iodine, and iodine can't replace anybody. And so this is important synthetically for a lot of reasons. So if you were to look into kind of drug design and synthesis, so iodine is used, and I mentioned this before, I think, but it's used as what's called a leaving group. And all that means is, well, we just went over iodine can be easily replaced. And this is also why iodine became a regulated substance after Breaking Bad. So Breaking Bad, you use iodine, and so remember we looked at iodine in lab. It's this nice, pretty, purple, shiny powder, and it used to just be available really readily. It was not a big deal. And then it became a regulated substance after Breaking Bad, and that's just because you can put it in there and then replace it with the methyl group to make meth. But yeah, otherwise synthetically it's used a lot because it leaves readily, you can replace it. And then fluorine is also good. So this is used in like drug development. So drug design, they often replace like fluorines in place of methyls. And so if you look at a lot of like antidepressants even, they have fluorine groups on them. So this is Prozac. And so the chemical name for it is fluoxetine here. And so you see there it has these 3 fluorines on it instead of methyls. And so this is just used in drug design. It makes it stable, and I think also helps it cross the blood-brain barrier. But they're very advantageous to use in drug design. So you see that often in drug design as they're trying to figure out how to put fluorines on there. And so again, a lot of that is due to its stability. And so now if we go over these reactions, we can see that yes, they would occur. So if you have bromine here, and so bromine is a liquid reagent, and that's why bromine and iodine are really useful synthetically. So we said iodine was a solid, so that's really easy to handle. And bromine, it is an angry, fuming liquid, but it's still a liquid, which means you can pipette it out, measure it, so it's still easy to handle. So fluorine and chlorine get more difficult since they're gases. So trying to work with these, you need like special gas regulators because they're going to eat through everything and destroy your life. And so trying to fluorinate something, again, is pretty difficult and dangerous. But if you need to do it, you need to do it. And so here we have our reaction. So we would form our sodium bromide and then displace the iodine. Then going up in this series, well, now we can take that sodium bromide, react it with chlorine, and that gives us sodium chloride and forms bromine. And this would probably leave in the nice form of reddish gas. And then, of course, fluorine now can replace our chlorine, so we can react it with, we could have done sodium chloride, or in this example, potassium chloride, and then make potassium fluoride and chlorine. And then this is like a safety note. So if you were doing some reaction and you expect to make a fluoride salt, so this is hazardous. And so we'll get to it later. But basically, we've mentioned HF is a weak acid. And because it's a weak acid, it has this equilibrium where it can go back and forth. So anytime you produce a fluoride salt, it has the chance of meeting up with a hydrogen floating around in solution. So if you're doing like an aqueous reaction, you would have protons floating around. They can then make some HF. And so you would want to neutralize this or something if you were actually planning something synthetically. You know you're going to produce some fluoride salt. You got to make sure you neutralize it, quench it, and treat it properly so that you don't form a bunch of HF. So here you could add a bunch of bicarb. So if you add a bunch of sodium bicarbonate, that would prevent it from being in acidic conditions so that you can't form a bunch of toxic HF that could do some damage. So that's a really helpful hint to keep in mind if you're ever planning something synthetically. And so now the double displacement reaction, I think we saw some of this in our copper reactions. And so double displacement, the first thing that we'll note about this, so there may be some exceptions, but they are generally not redox reactions. And so they're just kind of swapping partners around. So we have this general A, B plus C, D, and then we get new cation-ion pairing. So we get AD plus CB. But then the next question is, well, what drives this reaction forward? And so it depends upon the precipitation. And so let's look at something. So I need to print out more stuff for you guys. So, sorry, I'm trying to come up with an example. All right, so let's say you were doing this reaction. So if we had sodium acetate plus silver nitrate, what would happen? And so let's take a look of, well, first of all, what is going on in solution in our beakers? And so we have to think about this. So there's our little beaker. And so, of course, we put sodium acetate in solution. It's going to disassociate right away. So we have sodium ions floating around and acetate. And then imagine, let's say we've just dumped in our silver nitrate, so it hasn't had a chance to mix or anything. So right now we just have ions in solution. But then the next question is, well, what kind of a product will it make when these ions see each other? And then will it make something that's insoluble and fall out of solution? And so the issue with this reaction is, so let's say they're floating around, and then silver and acetate bump into each other. The question is, are they going to stay paired? So is that ion-ion interaction strong enough that it can overcome the solubility, or will it just stay in solution? And so to answer this, we have all these solubility rules, which, like I said, I need to print out this for you. And so we have all these rules. And so on an exam, you would just have to consult this chart. So if we look at this chart, we have these compounds are generally soluble. So lithium, sodium, potassium, ammonium, those are all soluble. And then take a look at this next one. Nitrate and acetate salts are also soluble, so no exceptions. So what this is telling us, okay, silver and acetate see each other, but then it's still soluble, so nothing happens. So then it just goes back to floating around, being an ion in solution. So in this case, there would be no reaction. So now let's see, well, what does drive the reaction forward? And so if we look at this example, so now it's slightly different. I exchanged out the sodium acetate for sodium chloride. And so now visualize the same thing. What could happen in solution with all these ions? So we have sodium, chloride, silver, and nitrate. So they're all floating around looking at each other. And so if we have sodium and nitrate meet up though, right, nothing's going to happen. Those are still insoluble, so we can go back to our rules. Well, sodium's always soluble, nitrate's always soluble, so that doesn't matter. But then our silver and our chloride, so what happens when they see each other? So now they're floating around, they knock into one another. So if we look at our solubility rules, so we have chloride, bromide, and iodide, and now these have exceptions. So now it says when these ions pair with silver, mercury, or lead, these compounds are insoluble. And so there we have it, silver. So once we make this silver chloride, that means that basically that ion-ion interaction is, now that's strong. So the solute ion interactions cannot overcome that. And so it drops out of solution. And so that is what drives the reaction forward, is the formation of a precipitate. And so then afterwards, right, we'd still have the sodium nitrate floating around, and then our silver chloride would start lumping down at the bottom or something. So that's why in some of those reactions that you do, right, you see a precipitate, that's what's going on, is you're making something insoluble, it's dropping out of solution, and it's continuing to drive that reaction forward. So then this drives the reaction forward. So we keep producing silver chloride until it all is done. And so the other thing that drives a double displacement forward is the formation of water. So driven forward by either precipitate formation or H2O. And so water is generally formed in the neutralization reactions. So we just look at a simple example. So if we take sodium hydroxide and add nitric acid to it, do our double displacement, so we get HOH, which of course is just water, plus our sodium nitrate. And again, it's a liquid, and so this reaction can proceed forward from our water being formed. So that will drive it to completion. And so now we have to be able to consult our solubility rules. And it's not too hard. It's just reading, and then kind of you'll start to remember the exceptions. There are some funny things that can occur. And so sulfate, so when sulfate pairs with strontium, barium, lead, silver, or calcium, the resulting compound is insoluble. And let's also put some numbers in perspective. And so I will say, so y'all are just getting like a taste of this now. So when we go on to winter quarter and spring quarter, I always forget where this happens, we'll revisit solubility because we're going to later get a much more clear definition. And so let's see what I mean by that. So if we look at calcium sulfate, for example, we have to even determine, well, what does that mean to be soluble or not? And so what you're looking at in Wikipedia or any other reference material would be the solubility product constant. And so this is telling you how soluble it is. You can also look at the solubility in water. And so this is kind of what I care about as well. So you can see this calcium sulfate, you can get 0.26 grams in 100 milliliters of water at 25 degrees Celsius. So not too soluble. Again, in our future quarters of chemistry, we'll revisit it, we'll use this KSB, and we'll actually quantify the exact amounts. So that's where we're going eventually. Question or?
Yeah, does that mean if you put in 0.3 grams, that some of it would stay as a solid?
Yes.
Okay.
Yeah, so you put 0.3 grams in solution, basically 0.26 would go in, that other 0.04 roughly would be hanging about, but then you would, you could do some math and figure all that out, like what your molar concentration then would be in solution. But yeah, we're not there. Right now we're just looking at our general rules, but I hate just giving rules and saying like, oh, these are the rules, and I will come up with an example where the rules get violated, and this is why. And so just comparing sodium chloride to see how soluble it is. So this you have 360 grams in 1,000 grams of water. So that would be like 36 and 100 to give you a comparison. So now that's way more soluble than our calcium sulfate. And then silver chloride, so we just said that was really insoluble. And so this is pretty insoluble. So this is 520 micrograms now in 100 grams. So you can at least start getting a taste of what that means to be insoluble. And so again, all this would be measured experimentally. And so then now going down at the bottom here, so these are now compounds that are generally insoluble, so hydroxides and sulfides. And of course the exceptions would be our first row, so lithium, sodium, potassium, and ammonium. So those are always soluble. Then sulfide with calcium, strontium, or barium tend to be soluble. And then this is where things can get odd with the hydroxide. So when hydroxide pairs with calcium, strontium, or barium, then the compound is slightly soluble. And sometimes it's still considered soluble. And then so phosphate and carbonate, those are generally insoluble unless it's, again, lithium, sodium, potassium. So, and so like we saw, so acid-base reactions are then classified as double displacement. So we saw that with the other example. So here's just another neutralization. So hydrochloric acid plus sodium hydroxide. Again, we form our salt. So of course our salt dough is in solution. And then our water here, I think this is written wrong. So that should be liquid and this should be aqueous. Oh, so let's go back to these solubility rules. So these solubility rules also dictate what little symbol I put behind. So if we go back to this reaction, so the sodium chloride, it has an AQ, not only because we know it's a little reagent in a bottle in an aqueous solution, but this AQ is telling us that it is soluble. So of course that matches with the rules. We said that sodium salts tend to be always soluble. So it's aqueous, silver nitrate. So if we look at our nitrate, remember those were always soluble. So we know that this is aqueous. So soluble. Then sodium nitrate has a little AQ as well. That tells us it's soluble. Again, ions in solution. But then the S here, that's telling us that it's going to be insoluble. So it's falling out of solution. That's why you write the little S there to indicate, yes, that's my precipitate. And again, that's going to be the precipitate. Let's see. So the last little bit that we'll touch on, so we do talk about redox, which is the last bit of our chapter. So oxidation reduction reactions, so that's our last bit of chapter 10. And so oxidation reduction, like we just said, that was a transfer of electrons. And so in this case, so what type of reaction is this first one? So combination. And so these combination ones, they might tend to be redox as well, since you're starting with things in their elemental form and then you're making a compound. And so let's look at their oxidation states. So what oxidation state is sodium in? So it'd be +1 in a compound, but remember it's in its elemental form. So 0, and then sulfur. So 0, and then what's sulfur in the product? -2. So remember, sulfur is in the group 6, so we expect it to always be -2 in our compounds. And so same thing down below. This is another combination reaction. What else could this be? There's another word we could use. Remember the little oxygen? What did that tell us? Combustion, exactly. So anytime we see oxygen, that might also be a combustion, so we would say this is a combination combustion. We could also classify it as a redox reaction then. And so what's the oxidation state of iron in the reactants? Someone whispered it.
0.
0. Oxygen? 0. And then iron in this compound? +2 or? So the oxygen's -2. So reverse your swap trick.
Oh, +3.
So +3, or set up your algebra. So -2 for our oxygen times 3 is equal to 2 times x, or -2 times 3 plus 2 times x equals 0, something like that for your algebra. And so now let's more formally go over oxidation reduction. So to convert a free element into an ion, that means that the atom must gain or lose electrons. So we've been kind of seeing that with our sodium chloride formation as well when we were discussing that. So sodium plus chlorine to give us that sodium chloride, right? We mentioned, of course, that sodium is losing the electron at the same time that chlorine is gaining one. So it's a nice handoff. And so, of course, if one atom's losing, the other must accept. We saw that. And so now we're just re-emphasizing this. So this would be a redox reaction as well, making our sodium chloride table salt. And so any reactions where electrons are transferred are just called redox. And so atoms that lose electrons are being oxidized. And then atoms that gain electrons are called reduced. And so back to our sodium chloride example. So we can look at our oxidation states. So sodium started off in the 0, went to the 1 plus. Chlorine started off in the 0, went to the -1. And so again, sodium gave up that electron, so it underwent oxidation. So it lost electrons, became positive, while chlorine underwent reduction, and it gained those electrons. Now there's two little mnemonics to help you remember. I'll give you two. So you can pick your favorite or none at all. And so I'm originally from Texas, and so we like oil there. So we have oil rig, and so that stands for oxidation is losing electrons. Reduction is gaining. And so maybe you're not a fan of the fossil fuel industry, or maybe you just like cute, fuzzy animals better. And in which case, I have Leo. The lion goes grr. And so that stands for losing electrons. Oxidation. And gaining electrons is reduction. So either one helps you remember. So again, losing electrons, oxidation, gaining electrons, reduction. And so of course we saw that, so oxidation, they're increasing oxidation state, so losing electrons, so they went from, in this case, so we're looking at the formation of carbon disulfide from copper and sulfur. So we see, why did I say copper? Carbon, so carbon went from the 0 to 4 plus oxidation state, and then sulfur went from 0 to -2. And then of course we see that the electrons are balanced. So this is a 4 electron process, but then we have 2 equivalents of sulfur. So 2 times -2 gives us 4. So that was 4 electrons being gained total. And again, reduction, decrease in oxidation state, so it's more negative. And so this is just a quick recap. And so oxidation states are not ion charges, even though they follow the same. And this also gets, when we have to assign oxidation states kind of formally. And let's look at some example. And so sometimes these oxidation states are more just electronic bookkeeping. So if you were looking at, let's say, a combustion reaction, so C818 plus oxygen gives you CO2 plus H2O. So obviously this isn't balanced right now. But let's just look at the oxidation state of carbon. Because this is where kind of the oxidation state being arbitrary comes more into play. So what's the oxidation state of carbon in our product? This one's easier to handle. Check it again.
I mean, 4 + 1.
Yeah, so +4. And then the question is, well, what about this carbon? And so let's go through it together to figure out how you would do this. So properly to do an organic structure, you'd have to like draw the whole thing out and then analyze it carbon by carbon. But we don't have that luxury here. We don't know what it looks like. We're just given this general reaction. And so to find it, again, this is for electronic bookkeeping purposes, we have to base it off of our hydrogen. So we know our hydrogen's 1+. And so now we can set up our algebra. So 0 is equal to 8 times x for carbon plus 18. So 1 times 18. And so now we have negative 18 is equal to 8x. And so now just solve for x. So what do we get? I didn't fire up my calculator. So negative 18 divided by 8. And so I get negative 2.25 for the oxidation state. And so that is fine. That is what it is for our, again, our bookkeeping purposes. And so we're just looking, right, this is the average oxidation state of all of them based upon the hydrogen. And so now we can tell at least who's being oxidized, who's being reduced. So oxygen, of course, starts off in 0, goes to -2. So was oxygen oxidized or reduced? So reduced. So it gained electrons. So it became more negative. And then carbon, so it went from a negative oxidation state to a positive now. So did it get oxidized, reduced? Oh, check that. So oxidized. And so we knew it was oxidized as well, since if oxygen is being reduced, that means the other one has to be oxidized. So they both can't be reduced, right? One has to be reduced, the other has to be oxidized. And then if we wanted to do our electron bookkeeping, we would first have to balance this equation, and then the electrons would make sense. And then so rules for assigning oxidation state, they should feel fairly repetitive. And so just to re-emphasize, so we saw free elements have an oxidation state of 0. So this is rule number 1, and don't forget it, so we keep using it. So again, anytime you see it in their elemental form, it's a 0. Then of course we know that most of the ions follow with their charge. So of course our first row alkali metals all tend to have that 1+ oxidation state, just like their charge. The halogens always tend to be -1, so chlorine, bromine, iodine, fluorine, we've seen that. Then of course we know the oxidation states have to equal whatever the sum of the atoms is, so this could be 0 or overall charge, like we've seen. For example, if we were to look at nitrate, so what would be the oxidation state of nitrogen? Try again, oxidation. So base it off, you have an overall charge of -1. We know our oxygens always tend to be -2. Try another number. I heard you just whisper. So set up your algebra. So with ions, right, we can't just do the swap trick, unfortunately. So set up your algebra. So we know there's 3 oxygens. They all have a -2 charge. Plus, I don't know what nitrogen is, but we know it has to equal -1. So then what do we get when we solve? Five. So nitrogen is 5 then for its oxidation state. And so that's how you could approach all your polyatomic ions and trying to determine what they are. So again, just base it off of, you know, oxygen is almost always -2. And so looking at the more rules, so again, group 1 metals, we know they're +1. Group 2, we know they're +2. So hopefully things are kind of reinforcing themselves. And then let's look at some oddities. So we don't have the exceptions here. And so these nonmetals, whoever's higher tend to take priority. So what this means is fluorine is almost always -1 for the oxidation state. And then hydrogen, we said it's usually +1. So what are the exceptions to this? Do you remember? What's the key word to look for? Or maybe what it's bonded to? Do we remember the term either metal hydrides or just hydride? So anytime you see a hydride, that's a hydrogen that's really a -1 oxidation state. And we mentioned those are kind of oddities. So aluminum trihydride or aluminum hydride. So this would be one exception. So we know aluminum's in the 3+ oxidation state, and so that means that hydrogen is -1. So again, this would be the only exception for hydrogens, is if you start seeing hydrides. And generally, again, they're metal hydrides, so it's hydrogen bonded to some metal. So maybe you could have an iron hydride. So iron would have to be in the 2+ state based off of this hydrogen being -1. And then oxygen. So oxygen is almost always -2. But let's talk about the one exception, and that's anytime you see peroxides. So peroxides are different, so they have a different structure. And so if you see peroxide, it's usually shown like this. So a peroxide is formally 2 molecules of oxygen bonded together with an overall -2 charge. But that means that each oxygen then has a -1 charge. So if you have, let's just look at H2O2, for instance. So that's hydrogen peroxide, just the good old hydrogen peroxide in your bottle at home, or we use it in lab too. And so we see hydrogen peroxide. Well, we know hydrogen has that 1+ charge, so 1 times 2 is 2+, but then this peroxide, again, just has the -2 charge for both of them. So each oxygen is -1, so -1 times 2 gives us -2, so that balances it out. So again, anytime you see peroxide, this is a peroxide, and so just watch out with that oxygen charge. So other than that, anytime we see oxygen, we know it's in the -2 oxidation state. And then the rest kind of follow. So our group 7s, and again, there could be weird examples. like with a bunch of halogen-containing compounds like II3 or II4. So those would probably have weird states. And then group 6, we know that they tend to be -2. Group 5, again, they tend to be -3, unless we saw for nitrogen, like in nitrite, so we saw that was +5. But again, you would want to base it off of whatever it's attached to. So in this case, ammonia, it's attached to hydrogen, so you know hydrogen's going to be 1+, making nitrogen -3. All right, how do we feel about all that? Questions? We have like 10 minutes to trying to pull up your homework too. So then let's look at 4 here. So which one of these would you expect to react? So we have bromine with potassium iodide. Would that react? And then iodine plus potassium bromide. So which one would react? So take a minute or two to do that. I'm going to try to send this over. So what do we get for this one? So would the first one react, the bromine plus potassium iodide? I see some nods, so yes. So then we make potassium bromide plus iodine. And so we said bromine is higher than iodine on the periodic table, so more reactive. What about this one though, iodine plus potassium bromide? Will it react? Yes, no. So I see some shaking of heads, no. So no reaction. So iodine is below bromine, so it can't displace it. So let's do 6 together, and we'll look at what a net ionic equation is. So take a minute or two. So it says we have a solution of silver nitrate is mixed with a solution of sodium chloride. So this is where the cumulative part of chemistry starts to come in. So we're not asking you explicitly how to name them or how to write formulas, but we need to know how to do this. All right, so for the sake of time, let's start looking at this. So we have to write out, so AgNO3, so we know silver is always in the 1+ state, so that's our silver nitrate, plus sodium chloride, and you want to add AQ to give us a white precipitate. So what's the white precipitate? So silver chloride. And so you want to kind of see, well, what are my two possible products? So it could be silver chloride. Sodium nitrate's, of course, my other product. But then this is where you consult your solubility rules. So which one is going to be insoluble? And so if you go, of course, now I lost my solubility rules. So if you go back to your solubility rules, well, you can see that sodium nitrate, so those always tend to be soluble, while we had said, so silver chloride, those are insoluble. So that's how we know who the products are. So then we can put an S here, an AQ. But now it says write a net ionic equation. So we didn't go over that, so let's go over that, and I actually need more space. So I'm just going to rewrite it for a second. And so the key part of a net ionic equation is we just want to see, thinking back to our little beaker, which ones are actually relevant. And so we're essentially going to write this. So silver. So Ag. And so again, thinking about what's in solution. And so anytime we have this little AQ, that means that we can write them as separate ions. And so for the net ionic, you can separate it out. So silver plus nitrate plus sodium plus chloride gives you silver chloride. So don't separate this one now because it has our solid, right? So it's our precipitate, so it's coming out of solution. So there's our solid driving the reaction. Then plus sodium plus nitrate. So they have that little AQ still, since they're just ions in solution. We're not actually going to be isolating a crystal of sodium nitrate, right? Not unless we do something else, but it's just an ion in solution. And so for the net ionic, you want to cross out ions that are the same on both sides. And again, really, we're just getting rid of the ions that are just going to be looking at each other in solution. And so that means we're going to get rid of the nitrates because it doesn't do anything. It just looks at the sodium. And then get rid of the sodium because, again, it's just looking, not doing anything. And then so that leaves us with the process that happened. And so all we really care about is that we had a silver ion in the 1+ oxidation state, reacted with the chloride ion. We don't even care what the counter ion was for chloride. It doesn't matter. Same thing, the counter ion doesn't matter in this case for silver. And they came together to form silver chloride. And so this is your net ionic. So just Ag plus chloride gives you silver chloride. And so a quick aside, so what if we were going to write a net ionic equation for our neutralization? So sodium hydroxide, AQ, plus acid gives us HOH. And I'm just writing H2O like HOH so we can see it better. So liquid plus NaCl, so aqueous. And so what would our net ionic equation be for this? Any guesses? So what's and so you could write it out all formally. So sodium plus hydroxide plus hydrogen plus chloride gives me H2O plus sodium plus chloride. And so now get rid of the ions that are the same. And that just leaves us, so all neutralization reactions end up with the same general form of some sort of H plus, your acid plus your base gives you water. And of course you could change the type of acid, change the equivalents, but it generally ends up just being the same form of hydroxide plus acid gives you water. All right, I think we have to stop there because of time. So we'll take a 10-minute break, come back, do our quiz, and then of course ask questions after you take your quiz or whatever. So I know we kind of covered a lot. So just ask the questions. All right, so take your 10-minute break and then we'll start our quiz at 11:30.
Is the quiz number 6 or 7 or both?
It's like naming. It's got 1 coulomb calculation, a little bit of electron configuration, radius size, formula naming, ionization energy and electron affinity, lattice energy, some more naming. There's not too much math.
You say that. So you have a question about math. So last night I was looking at, for this problem with the ERXN, where do I get these numbers? The I2, these. Where do I get these numbers?
So those would just be the ionization energies.
They don't match the ones in my book.
Which ones don't match?
Well, like these. Yeah. So is it because you took 2 of those? I was trying, I watched a bunch of YouTube videos. I just was super lost. And then I looked on the homework and I was like, I don't understand.
So I'm not sure where they pulled that value.
Okay. But you just used them from here.
Yeah, but then like for this one,
Yeah,
you should
understand.
just be able to find, and I would have to look at your book to see
I know, I
what
didn't
charts
bring
it
my
has.
book.
I know I don't even have a copy, but if we just look up, so like sodium,
Yeah,
so we want the ionization energy for sodium, right?
yeah.
Ionization, oh my gosh, I can't type. Oh, and I should stop the recording.